Next up, I want to describe a pretty cool construction, and it's very interesting. So this is going to be called stereographic projection. And before I get to the two-dimensional case, it's going to be easier for me to draw the one-dimensional case, and then I'll need some pictures for the two-dimensional case. And we'll see what this has to do with complex numbers in just a second. So this still has to do with the infinity in the complex numbers. So for stereographic projection, here's the idea. Imagine that you have, so let's draw a horizontal axis, and then I don't care if we actually put the y-axis there or not. But what I want to do is I want to draw a circle, and we're going to draw, this is going to be a circle of, say, radius 1. And you can put it actually anywhere you want. But the customary way to do this is to put it so that the equator of the circle, the halfway point, is on the horizontal axis. Okay, and we can extend this axis down if we want to. But the idea is pick a point that's on the circle that's not the North Pole. The North Pole is special. We'll talk about that in just a second. But pick a point on the circle that's not the North Pole. Say this point, let's say this point here. Okay, so nothing special about that point, but let's just pick that point. And then what we're going to do is we're going to draw a line segment between the red point and the purple point on the circle. And in our case, this is what that segment looks like. And then what we're going to do is we're going to look at what's the point on the horizontal axis that intersects that line segment. And that looks to be about here. Okay, so that looks to be about here. And so if you think about this, for any point on the circle, pick any point that you want. If you pick different points, you're going to get different projections onto this horizontal axis, onto the x-axis, right? So if you pick a different point, say if you pick a point over here, I think it's helpful to look at an example where you have a point that's above the axis. Your line segment is still, I've got to zoom in just a little bit. Your line segment is still going to go below the circle here. But what it's going to do is it's going to project all the way over here. And so your projection point is going to be somewhere over here. And so it turns out that there's a unique one-to-one correspondence, so a bijection in mathematical lingo, between all the points on the unit circle except for the North Pole. So all the points on the unit circle except for the North Pole, they can be mapped uniquely to the horizontal axis. So pick a point on the horizontal axis, draw a line segment from that point to the North Pole. That's going to give you a unique point on the unit circle. And so what this tells you, if you've taken a foundations of math or a discrete math class, or if you know about countable and uncountable, what this tells you is that there's a one-to-one correspondence, a bijection between the unit circle without the North Pole and the horizontal axis. It turns out that there is no place for this North Pole to go. And we'll fix that when we talk about the two-dimensional version of this. By the way, if you want to get to the origin, the point that you have to pick is the South Pole of the circle. And then when you draw the line segment, the place where it intersects is the origin. But literally every point on this horizontal axis can be put into one-to-one correspondence with the unit circle, except for the top point, that North Pole. Okay, so that North Pole is special. So it doesn't matter how hard you try, you can never quite get all of the points on the circle to go into one-to-one correspondence in this map. Okay, so this is called a stereographic projection. What we're going to do is we're going to do this, but in 2 dimensions. Okay, so instead of thinking about just a circle sitting on a horizontal axis, what we're going to do is we're going to take a plane, and then we're going to put a sphere of radius 1 so that the equator line of the sphere is on that horizontal axis. So here's where I will need some technology. So this is the picture that we're going to think about here, but the process is going to be the same. So you have the North Pole, Okay, so we have this special point, which is the North Pole, which we can basically ignore for now. You pick any other point on the sphere, okay, and then you draw the line segment from the North Pole to that point, and you keep going until it intersects that plane, the XY plane. Okay, and so this is called stereographic projection. Okay, so this is stereographic projection. Okay, there's a formula in the book that you can look up if you'd like. I'm not going to worry too much about it, but there's a formula that you can look up that tells you if you pick a particular point on the sphere, what's the point that you get mapped to under this projection, right? So there's a formula for that that's well known, and I'll leave that to the book to the details there. So if you want the details, look at the book. Is what I mean. So again, this is called stereographic projection. You have a unique correspondence between this entire sphere minus the North Pole. So take the whole sphere minus the North Pole, and there's a bijection between that set and the XY plane. Okay, so there's a unique one-to-one correspondence there. Now, what we can do differently in the two-dimensional case, when we're thinking about the plane, we're thinking about the complex plane, of course, which is why we're talking about this in this complex analysis. But what we can do is we can assign the North Pole to get mapped to infinity. And so if we take the entire sphere, any point besides the North Pole gets mapped onto this plane, and then we can map the North Pole onto our notion of infinity. And when we do that, we get what's called the Riemann sphere. So this is now a way that we can talk about the set of complex numbers plus infinity, which has a name. So this is a way that we can talk about what's called the extended complex plane. And the extended complex plane is going to be denoted, typically it's denoted C star. I can't remember which one the book does, but there's two definitions that get used. Usually it's either C star or C hat. But what this is it's going to be the complex numbers, so the usual set of complex numbers, plus, so we'll take a union, infinity. Okay, so this is one way to think about the complex plane. The reason for doing this is that this allows us to treat infinity almost like we treat any other number, but we have to extend our usual algebra rules in a certain way. So here's what I mean. We have the following algebra rules now. If we take infinity plus a complex number, we get infinity. And of course, this addition is commutative. None of these definitions should be taken for granted. You should think about the fact that this is always the case. And if you wanted to formally think about these rules, what you could do is you could think about if you had a limit of, say, f plus g, where f goes to infinity and g goes to some value a, then f plus g goes to infinity. Okay, that's a way that you can formally think about this, and then analogously for the rest of the rules. If you were to have any complex number times infinity, that's going to be infinity as long as a is not 0. Okay, if you pick 0 times infinity, that's still indeterminate. Okay, if you have infinity times infinity, I should get rid of these bullet points in the front because they look a little bit misleading. Let's give them numbers here. If you have infinity times infinity, that's going to be infinity. So that seems like a reasonable concept, but again, the way that you interpret that is through limits. If you were to have any complex number and you divide by 0, you can now think of that as infinity. And this is special to the extended complex plane, right? If you have a non-zero number divided by 0, in the real case, say in the Calc 1 case, just to go to the simplest, your non-zero over 0 is going to get, you can think of that as kind of corresponding to a limit where the denominator goes to 0, but the numerator doesn't. And those limits are going to tend to be plus or minus infinity, or they won't exist. But in our case, for the complex numbers, since we only have this one version of infinity, we can just call that infinity as long as a is not equal to 0. And then analogously, if you have a over infinity, that's 0. So this fifth rule does actually hold when you think about analogs in the real sense. So if you were to have a over a really large number, whatever your a is, this is going to go to 0. Okay, so this is called the extended complex plane. This is a nice way that you can kind of formalize how this works. Before we end this video, what I want to do is I want to show you just a few pretty pictures that involve the extended, that involve kind of stereographic projection. Okay, and so I've already showed you a few pictures here. Let me actually just show you. This is the kind of definition of the stereographic projection. So you again start at the North Pole, connect a line segment with any other point on the sphere, figure out where does that line segment intersect the XY plane, and then that's your map. So you map this point on the sphere to this point on the plane. And then if you were to draw some shapes on the sphere, this is not exactly the same map that we had before, because now the sphere is actually above it, but the process is actually the same. It actually doesn't matter how far above or below the, well, it doesn't matter how far above the XY plane you are. Okay, you get a slightly different map, but it's basically the same idea. And if you were to do this onto, say, the globe of the Earth, this is what this weird map would look like. So this is one way that you can actually get a nice specific bijection between a sphere and a plane, right? So if you wanted to look at a projection of the Earth onto a flat two-dimensional map, this is what it looks like. Now, of course, this is a terrible idea if you're looking for an accurate description for, say, navigating the globe with boats, right? If you're trying to get around the world and navigate, this totally just loses many of the important things like proportion. And so things get very stretched near the North Pole. So if you think about where the set of points nearest the North Pole goes, those go all the way off to infinity, right? And things just get absolutely stretched beyond recognition. But you can do some other cool things. So there's some mathematical toys that you can buy where if you wanted to do a projection. So here's an example of stereographic projection. So this person's holding a flashlight where the North Pole of the sphere would be. And then this sphere is built in such a way that the projection lines following that, the map of the stereographic projection has that certain formula. And if you actually go through the formula and you want your projections to be horizontal or vertical lines, just this grid, this is what the sphere would have to look like. Okay, so again, this is stereographic projection.